Hi everyone, I'm Youyou. I'll be talking about a continuation of my PhD work, which I did with Kenichi at Ochanomizu University. The problem we have been solving is how to combine dependent types and effects. Having dependent types and effects in a single language is useful in two ways. First, we can build effectful programs that are correct by construction. This is done by encoding into types the properties we would like the program to satisfy. Second, we can verify the correctness of effectful programs that are potentially wrong. This is done by providing a proof separately from the program. There are several languages that allow us to do both of these. Two notable examples are F* and Iris. In these languages, we can use primitive effects and define custom effects in a dependently typed setting. As an approach to integrating effects into dependently typed languages, I designed in my dissertation a dependent type system for the delimited control operators shift and reset. There are two important design decisions. First, we restrict types to depend only on pure terms. For instance, we may have a list type that depends on a natural number, but not one that depends on a shift term. This purity restriction is necessary for maintaining the consistency of the language. The second design decision is that we compile programs using a selective CPS translation. That is, we only convert effectful terms into CPS and keep pure terms in direct style. The selectiveness of the translation makes it easier to prove type preservation of the translation. In this work, we extend my PhD work with an interesting feature, namely conditionals whose branches may have different types and effects. This feature was actually suggested by an anonymous reviewer of our past paper submission, and it allows us to reason about effectful programs in a fine-grained way. As a motivating example, let's consider the function f here. This function performs a control effect if the argument is 0, and it returns a pure value in other cases. So the two branches have different effects. The then branch is effectful, and the else branch is pure. When we have such a function, we typically cast the else branch to effectful and treat every application of the function as an effectful term. But if we do that, we lose the information that the function may not perform any effects, which could be used for verification and optimization. So ideally, we would like to accept this kind of partially effectful conditionals as is without casting the pure branch to effectful. One way to do this is to give a conditional type to the conditional term. Then we can treat an application of f as a pure term when f is called with a non-zero argument. Now the question is, how can we support partially effectful conditionals? This turned out to be a hard question, and we haven't been able to figure out how to solve it. So we would like to invite you to help us find a solution. In the rest of this talk, I will explain how I designed the type system and CPS translation for a language without conditionals. And then I will show you how things get tricky when we extend the language with conditionals. Okay, so let's begin with a language without conditionals. In the type system of this language, we use a typing judgment consisting of a typing environment gamma, a term E, and a computation type C. A computation type is a pair of a value type and an effect, which is either iota, meaning that the term is pure, or a value type alpha, meaning that the term may capture a continuation whose return type is alpha. Using this typing judgment, we define typing rules in a way that they assign precise effects to terms. As an example, let us look at the rules for application. There are two typing rules, and each of them takes care of the dependency of types and compatibility of effects. The typing rule on the left forms a dependent application. It requires the argument E2 to be pure because it appears in the result type, and we only allow pure terms in types. The rule also requires the effects of the subterms and the effect of the whole term to be compatible. The compatibility relation holds if all effects are pure or all non-pure effects are the same. The rule on the right forms a non-dependent application. It allows the argument to be effectful, but it requires the function to have an arrow type so that the argument does not appear in the result type. And it checks the compatibility of effects like the other rule. We define the typing rules for other constructs in a similar way, and guided by these rules, we define a selective CPS translation. Here is the translation of dependent application. We define the translation on the typing derivation because we need the effect information of subterms to decide how to translate the whole term. In the case of dependent application, we have 4 compatible combinations of effects, so we have 4 different CPS images. The first one is a direct style application, which we get when all subterms are pure. The remaining cases are a continuation taking function, which means that the original application needs access to the continuation. Note that in all of the 4 cases here, the argument E2 is kept in direct style because it is a pure term. We can prove that the CPS translation preserves types. The proof is by induction on the typing derivation, and it is simpler than the type preservation proof of a non-selective CPS translation. In particular, we don't need to extend the target language with non-standard typing and equivalence rules. All right, now we extend the language with partially effectful conditionals. We use the same typing judgment as before, but we may now have a conditional type in the type part of the judgment. The conditional type is introduced by the typing rule for dependent if, which is shown on the left. Like the dependent application rule, this rule requires the test term E1 to be a pure term as it appears in the result type. But unlike the dependent application rule, it doesn't check the compatibility of effects as it allows any combination of the computational types C2 and C3. We next look at the rule for non-dependent if, which is shown on the right. Like the non-dependent application rule, this rule allows the test term to be effectful as it does not appear in the result type. Also, like the non-dependent application rule, it performs compatibility checking, but this checking becomes harder in the presence of conditional computation types. The reason is as follows. For the compatibility relation to hold, the branch's effect must be either pure or alpha. To decide whether this requirement is satisfied, we need to normalize the computation type C2, which might be a conditional type, to a type effect pair. However, this normalization is not always possible. For instance, if C2 is a conditional type whose test term has a free variable, the type does not normalize to the required form. We could simply reject the term in such cases, but that would be too restrictive. Indeed, the example of C2 here is acceptable. Although we don't know if the effect is iota or alpha, we know that it must be either of these. So it seems that we need to do some careful analysis in the compatibility checking. That's the challenge with typing. Then what about the CPS translation? Here is the translation of non-dependent if. We have two cases corresponding to the two compatible combinations of effects. But what if we accept a conditional type like this? We know that the type normalizes to either of the two cases at runtime, but we don't know which at compile time. What this suggests is that we might need to use a CPS semantics to evaluate programs dynamically rather than applying a CPS translation statically. Then we don't need to deal with computational types with free variables. So that's what we currently have. Our finding is that partially effectful conditionals make it hard to type and CPS translate programs. We think that the challenges we face are not specific to this language feature, and we believe that someone has solved similar challenges elsewhere. If you have any suggestions on which work we should look at, please let us know during Q&A. Thank you.